Okay. Wow, it's really struggling today. All right. So what we're going to do is go over acid-base behavior and chemical structure. Basically, the idea is if you can kind of get the main idea here on how the structure of a chemical influences if it's an acid or a base, will make your life a little bit easier down the road. So I'm going to give you guys some things that influence acidic behavior. I'm going to give you some things that influence alkaline or basic behavior, and then we'll kind of tie it all together. That's our goal. Okay. So there's three factors that influence acid strength, and a lot of the times, being a strong acid versus a weak acid is kind of a combination of these three things. It kind of depends on what type of acid you are. Okay, so the first thing is to look at the polarity of the things that are attached to the hydrogen. And when you look at polarity, you're going to look at electronegativity. That's what EN stands for, electronegativity. So basically, electronegativity is how well things hog electrons. Here are three different types of bonds with H. In one of them, it is an acid. In one of them, it is a base. And in one of them, it's kind of a neither. Okay. So hopefully by now you guys can identify that the HCl is the acid. The other two, though, it's a little bit more difficult. And this would require you to kind of remember where the trends are, like who's very electronegative, who doesn't really care about electrons. We would say that the metals don't really care that much. And then carbon's kind of somewhere in between. So to give you guys some electronegativity values, hydrogen is a 2.1, chlorine is a 3.0, sodium, I think, is about 0.7, and carbon's about a 2.5. So the idea is that chlorine can hog electrons, and by hogging electrons, it's okay with H leaving and leaving its electron. So this guy would be the thing that would produce the H plus, right? Since sodium, it has a very low electronegativity, it's okay with hydrogen stealing that electron, and that actually is a base, something that we might tackle down the road. And then this guy right in the between, it doesn't really do anything. They just kind of share, and it's a non-polar bond. So polarity is kind of one of the things, right? But it's not just that. You got to look at some other stuff. The second thing is the strength of the bond, because if you think that polarity is the only thing, you're going to run into some issues. You're going to run into some issues when you look at like HF. We'll talk about that today. So the strength of the bond. A stronger bond will dissociate less than a weaker bond. Okay, strong bonds dissociate less than weak ones. So that is to say, if the bond's really strong, it's really going to hold on to that H very well. So if you just thought polarity was the only thing that influenced acidic strength, you'd say, all right, well, HF is a super strong acid. But you guys know, because you can look at the chart, HF is actually a weak acid. So it's kind of a combination of these two things. HCl, Cl is just polar enough to be able to hog electrons, but not so polar that it holds on tightly. So this thing can break into H plus easier than this guy because fluorine and hydrogen are a very, very strong bond. Okay, so it's kind of like a you got to be polar, but you can't be too polar. It's a weird thing. Okay, so those two things influence how strong an acid is. And then the last thing that we're going to spend some time on is looking at the stability of the conjugate base. And think of this as, what do the leftovers look like? So how stable is the conjugate base? Is it cool with having a negative charge? So the more stable the base is, the stronger the acid. In other words, if the conjugate base is cool with the H plus leaving, all right, it would totally endorse that and make that a stronger acid. So if the base part is more stable, it's more likely to ionize H pluses. So what we're going to look at today is some things that kind of lend to stability, right? Like I said, there's no real calculations in this. This is difficult to teach online, right? So an acid strength is a combination of all three of these things. Typically, if you are a binary acid or two things, it's the first two things that matter. And if you're like one of those big ones that have oxygen, we call those oxyacids, it's kind of this third thing that determines the strength. All right? Is there any questions about what just happened there? So in other words, who gives up H pluses better, right? Things that give up H pluses are things that are polar, but not so polar that it makes a strong bond, and things that have stable leftovers. So that's kind of the idea behind that. Now, the binary acids, the bond strength is kind of the most influential factor in determining the acid strength. You're looking at the strength of the bond. So this shows up more in binary acids and oxyacids. By the way, what's a binary acid? A binary acid is two things. So there's not very many options for binary acids. You've got HF, you've got HCl, you got HI, you got HBr. Those are binary acids. Okay. So bond strength is kind of the major player that makes these things determine who's stronger. We already talked about HCl and HF. HF is a stronger bond, therefore it cannot quite ionize those H pluses as well. Okay. Like I said, I'm just kind of cruising through this. If you need anything, need me to slow down. All right. Now, the big topic of today is the oxyacids. Okay. Now, this chemical is not written like this in your book. This is acetic acid, but I wrote it this way because this is what old school professors write it as. It's its structural formula. But I also wrote it this way because I'm going to show you guys how the Lewis dot structure of this influences this thing's acidic behavior. Okay. So I'm going to go ahead and the thing is that a lot of times, and this takes practice, just being around science and chemistry and biochemistry a lot more, it's sometimes tough to tell if something is going to be a base because of the OHs or an acid because of that H, right? So when we look at the Lewis dot structure of this thing, I'll just go ahead and draw it real quick. Okay, so we have CH3, CO, H. Okay, so that's the structure. And what you guys are going to start looking for, and by the way, this COOH, you learn that in biology, maybe in anatomy. It's a biochemistry thing. It's called a carboxylic acid group. Basically, the idea is this. You're trying to figure out, will the OH leave or will just the H leave? Now, you know this is acetic acid, so you guys already know that this H is fine with just taking off, right? The question is, why does only the H go? Why doesn't the O go as well? So here's going to be kind of our general rule that you guys are going to use to figure this out. So the question is this going to form H plus or OH minus? Here is the general rule. If the OH is attached to a metal, then the OH is going to leave together, right? If the OH is attached to a metal, metals have low electronegativities, metals are okay with just the whole group leaving. Now in this thing, the OH was attached to a non-metal with a high electronegativity. If the OH is attached to a non-metal with a high electronegativity, okay, and when we say high electronegativity, we're kind of like in the 2s, somewhere around there, or close to oxygen, another oxygen, then an H plus is going to leave. So the reason why this thing ionizes as an acid is because this OH is attached to a carbon that's attached to an oxygen. Okay, so that's one of the things that if you ever take biochemistry, you're going to have to kind of like sort through and deal with. Okay, so is it an oxyacid or is it a base? That's kind of the general rule. And by the way, this doesn't have to have a super high electronegativity. It has to be like as at least carbon. Okay, so somewhere in the 2s, right? So now what we're going to look at is determining how strong oxyacids are. Thing is that you guys can just use Appendix D and look up how strong these things are, these weak acids, based on their Kas. But if you don't have access to that chart, there's a couple of little tricks that I'm going to show you with oxyacids. The first trick, all right, and by the way that this is written for XOH, okay, so what X is just some element, right? It could be a whole group of things. It could be a single element. It doesn't really matter. It's just when you're looking at oxyacids, usually they are groups of things. So like HNO3, HNO2, HNO3, things like that, right? So for XOH, you're going to look at the electronegativity of X and the number of groups attached to X. So this is kind of our main idea. There's two things that we're going to look for. Now, if you cannot remember electronegativity, it's not a big deal. It's in the book. I have no idea what page it is. Some of you guys have your books marked, or maybe you don't have that. You don't have a book because you didn't come in and grab a book. I will post, and you guys could Google it as well, but I will post, or I'll try to remember to post the electronegativity chart that's in our book so we're all on the same page. So if you're an oxyacid and you have the same number of OH groups and the same number of O atoms, the acid strength increases with an increasing electronegativity of X. My God, that is a lot. Like, what does that even mean? Probably easier to see an example of this. Okay, so here's an example. We got H-Clo, we got H-Bro, we got H-IO or HIO, right? So the question is, which of these three acids is the strongest out of the weaks? Well, like I said, you guys could go ahead and you could look at Appendix D in the back of the book, and Appendix D in the back of the book definitely says out of those three, the HClO is 3 times 10 to the negative 8th. The H-Bro, which is not even in here. So I guess we're screwed on that deal, right? So the question is, how do I figure this out? Well, you're going to use this rule. And the rule is you're going to look at what this is bonded to, okay? So if I had to draw the Lewis dot structure of these guys, basically it's this: Cl, O, and H. That's H-Clo, right? So the question is, who's the strongest acid? Well, you would have to look at the only thing that's different about these guys is that element and its electronegativity. So the idea is the thing that is more electronegative will produce the stronger acid. So out of Cl, Br, and I, I'm just going to go ahead and let you know, if you're looking at a periodic table, I am. Chlorine is more electronegative, okay? It's like 3, 2.8, 2.5, or something like that. I don't know. But all I know is this. Chlorine's more electronegative, so this guy is going to be the most acidic out of that group, which means this guy is second, which means this guy is last. I don't know if that makes sense to you guys. Okay? So that's the first thing. If you don't have the chart, or these things aren't listed on a chart, you can figure out who's more acidic just by looking at chemical structure. So that's rule number one. Rule number two is if the oxyacids have the same X, the acid strength increases as you add O's to the X. What does that even mean, bro? All right, so here's our Clo groups: H-Clo, H-Clo2, H-Clo3. So the rule is, as we get more oxygens, it becomes a stronger acid. Now, the reason that helps make something a more strong acid is because every time you add an O, it makes the conjugate or the leftovers a little bit more stable. It produces kind of a resonance structure that allows them to kind of like share the burden of that extra negative charge. So out of these guys, we would say this is the strongest acid out of the group. This is second. This is third. Just because, and by the way, if you looked at your strong acid chart, that's listed as a strong acid. So that must mean that that little booger is the strongest out of all of them, which it is. Okay? So oxyacids, there's two things to look at. What's attached to the O's and how many O's are there? That will make the stuff way easier for you. Okay? So that's kind of a general idea on how to put all this stuff together. We're going to do a couple of sample problems, and I'll show you guys how to kind of like think your way through this stuff. Okay? So our goal is to rank the following in order of increasing acidity. So we're going to go with most base-like first to most acidic, increasing acidity. So out of this group, we're going to find the thing that is most like a base. All right. All right. So we got these 4 things. Oh my God. What are we doing here? Okay. So these are obviously not oxyacids. These are more binaries. There's only 2 different types of elements. So what we got to look at is we got to look at bond strength here. Kind of look at kind of what they're attached to. Also, you can just look at how they're written. A lot of times, I mean, heck, you guys already know out of this group who's probably the most acidic just by looking at how the formulas are written. All right? So out of these guys, I would say the most acidic thing is the HI because it's freaking hydroiodic acid, and that's a strong acid that we know. It's on our chart. Okay? So we know that this is the most acidic. Now, the rest of this stuff, it's going to be kind of tough, right? So we're going to have to kind of use our brains a little bit. And it would help if we had an electronegativity chart in front of us, which I will help you out with that, okay? So I would say probably the next thing I would do is try to figure out who's the most base-like, okay? So let's see here. You might have to have a periodic table in front of you here, all right? So we're basically looking at, all right, that guy, and then the O here as well. Who's going to be kind of next in the list, right? So I'm going to give you guys a second to grab a periodic table. I'm just going to go ahead and pause this, guys, so we're not wasting time here. All right, resume. There's a huge lag here. All right, so here are the electronegativities of these things. All right, so sodium's electronegativity is 0.9. Okay, it's 0.9. I was wrong on that. 0.9. Oxygen's electronegativity is 3.5. All right, and then crap, I lost my page. AS is 2.0. Okay, so 3.5, 0.9, and 2.0. So what we're looking at is typically, like I said, if you're looking at polarity, you got to be, pretty electronegative to be an acid, but not so much that the bond is really, really strong. So I would say that the thing that is going to be able to hold on, that would be able to hold on to electrons the least would be the sodium. So the NaH is going to be the most base-like. Okay? So following this trend, let's see here.
I have a stupid question.
You don't have a stupid question because this stuff is hard. What's up?
So if you look at the chart, isn't the I 2.5?
It is 2.5.
Then why is it the most acid-like?
Because you would think that the water would be the most acid-like, right?
Yeah.
Because so the thing with binaries is it's got to be a combo meal of polarity and bond strength. So this one's the most polar, but that's an also pretty strong bond, right? So That's tough though. Like, how the heck am I supposed to know that? What you're supposed to do is draw on prior knowledge that that if something's written like that and it's a strong acid, that's going to be the most acidic. Does that make sense, Jay?
Yeah.
Okay. So, yeah, I totally get it. You're like, well, what the heck, man? That's supposed to be the most acidic because it's the most electronegative. Well, it kind of crosses that threshold of, like with fluorine, it's too sticky. It's too strong of a bond. So I'm going to put water here, and I'm going to put that there. That's how you rank those things. Like I said, that's really hard. I think that's hard. Okay? That was a really good question. Somebody else have any questions about that? All right. Next one's going to be way easier. You'll see why. Next one's way easier. All right. So when I look at this, I don't even know what this acid is called. It doesn't even matter. I just know that that looks like an oxyacid to me, and that looks like an oxyacid to me, and that looks like water. So I'm going to guess these two little boogers are more acidic than water because of the way they're written and the fact that they're oxyacids. So I'm going to say that water is the most base-like. And I would say that the only thing that's different about these guys is that this oxyacid has one more O. Oops. So there you go. That one's a little bit easier. Are there any questions about that? So most
I'm good.
You guys are good? Okay. All right, there you go. That's pretty much the lesson. I think there's one more slide. Methanol versus acetic acid. Yeah, I'm just going to go ahead and talk about this just because it might come up. I don't know. I mean, I'm not really worried about this. But when you look at methanol versus acetic acid, the reason that methanol is not an acid and acetic acid is because of the stability of that carboxylic acid group. For whatever reason, that thing is a more stable base. Okay? The extra O can hog electrons to stabilize the conjugate base, and the resonance of the conjugate base means it's more stable. So it can kind of share the burden. So a lot of times, things that might look like they're acids or bases might not be because they don't have this extra resonance. All right? Okay, so that was fast and furious. I'm going to stop this.